So let us start the course of lectures of Professor Zhan Shi, the professor from Blanching. You see the subject of his lectures, and we can start, I think, because most of us know Professor Zhan Shi.
Okay, thank you, Misha, for the introduction. So, thanks to all for coming. It's a great honor to be here. At the beginning, when I first came to St. Petersburg, it was big. I mean, for me, somehow the city was synonymous with three celebrities. Dostoevsky, Tchaikovsky, and Michalevich. And now I think I will be able to tell myself that it will be also for professional reasons, because I have been an active member of the institution, certainly only for 3 months, but well, it will be it will have been a very special period in my life. When I say institution, I mean the set of, so the Chebyshev laboratory, we are here, the State University, the Chekhov Institute, and the Euler Institute. Yeah. Okay, so I wish to talk about branching random walks. It's maybe there will be 5 lectures, so there are 2 this month, so it's today and then next Thursday, and unfortunately I would not be here the Thursday after for some special reasons. And in May there will be 3. Okay, so today we start with introductory parts. So let me start with the best known parts of branching random walks, namely branching Brownian motion. So if we do probability theory, probably we realize that I think it is the most fundamental subject is sum of independent random variables. And well, it's more or less it more or less corresponds to branching random walks if there is an additional branching mechanism in the system. And for sums of independent random variables, we all know that under some integrability assumption, if you take the scaling limits at the end, what you get is a so-called Brownian motion. And here there is something very similar. There is a corresponding continuous time system which is associated with branching random walk, and it's called branching Brownian motion. So from this point of view, both of them play fundamental roles in the study of branching process. But it's in principle, we can say much more about the continuous time setting. So let me define a standard branching Brownian motion. So its one-dimensional time is continuous. Let's say it starts from the origin. So this is space. This is time. So at the beginning, I only have one particle starting at the origin, and it's a standard one-dimensional Brownian motion. Okay, and everybody has a finite lifetime. So and the lifetime is random. It's an exponential random time. So let's say of parameter 1. So after a random exponential time, then the particle dies, and when it dies, it splits into, let's say, 2 particles. So now I have a pair of independent Brownian motion. This is one, and the other one does independently. Both start from the place where the father dies. And each of them has a random exponential lifetime. So let's say this guy dies, and it gives birth to 2 independent ones, and so on. So if this one dies, okay, so let's look at what happens, let's say, at time t. So in my picture, at time t, there are 4 particles living in the system.
Exponential time is the same for all children.
Well, everybody, the lifetime for each one.
Always the same for all children. Yeah.
Everybody's lifetime is exponential 1, but they are independent.
Yeah.
Yes, but the same distribution. So I write the positions of particles at time t. So these are positions. And capital NT is the number of particles alive at time t. So in my picture, capital NT is 4. So I have this whole bunch of random variables. And let me define. So I write a function f, which is the indicator function of x to be non-negative. So it means that it's 1 if x is positive or 0, and it's 0 otherwise. And I would define a new function which has 2 variables, time and space, so which I called u. So it's a function of the pair time and space. So I defined it. Double dot means is the definition. Okay, I defined the function u as the expected value. I take the products over all the particles alive at time t of f of small x plus the position. So for each positive time t, for each special, for each variable x in the space, so this is for positive t and for real number x. I hope the well-definedness of this quantity is clear because f is bounded. So the product anyway is between 0 and 1, so I can look at the expected value, right?
But it's just a probability, right?
Sorry? Yeah, in this case, actually, it's just a probability because it's, well, I write it here because actually, for the moment, the only thing I need here is the boundedness of f. I mean, I don't need any particular property of this function f. Okay, so far I think so good. Now I'll do some computations for this function. The expected value implicitly I have the constant 1, and I make a discussion between. So look at the first time I have this, whoops, this branching time. I'll write it capital T. It's the first time when there is a separation. Yeah. So I make it. Oops, sorry. I make a discussion between when it happens, whether it's before or after time t. Okay, why not? So in the first case, I look at what happens before. And in the second situation, I look at the case when it happens afterwards. Otherwise, nothing changes. Oops. Okay, so I realize that in the second situation, things are very easy because I'm in the event when the separation comes after time t. Capital Nt, by definition, is the number of particles at time t. So at this time t, actually, there is only just one single particle, the original one, nothing else. So in this product, actually, there is only one. And by definition, by assumption, the capital time t is totally independent of the trajectory of the x1, which is just a usual Brownian motion. So in this second case, actually, this expectation is very easy. It's the product of the expectation of this indicator function and the expectation of f of this one. So the first one is just probability that capital T is greater than small t. It's the tail distribution of a standard exponential time times the expected value of f of x. Well, I think I prefer to write capital BT, whereas capital B is a standard Brownian motion. So this is the value of the second expectation. I mean, there is absolutely nothing particular to say about that. Yes? And actually, the first piece is also very easy. So now let me work on the first piece. It's also very easy to work out its value because I know the distribution of this capital T, which is exponential. So, okay, I'll integrate with its density function, which is e to the s ds. Yes? So I put myself into the event that this first splitting time happens exactly at time s. Well, actually, between s and s plus ds. And now I look, and everything happens afterwards is totally independent of this s. So now I look at expected value of this product. So let me come back to the picture again. By assumption, what happens after capital T is just two independent copies of Brownian motion. So the only difference is that, okay, now I have two Brownian motions, and they are completely independent. And of course,
you always consider that the branching is the passage from one particle to two.
Yes.
So it's at this point you only consider the simplest.
Yes, yes. Okay. So if you prefer it each time to have three, then okay, there was something changes a little bit.
Just wonder what we are considering now.
Yes, yes. So for the moment, I'm looking at the simplest case. The branching is binary. Yes. So at this time, which is small s actually. So I have two independent systems of Brownian motion, and both start from this point, which has the distribution of the Brownian motion at time s. Yes, and that's it. So I know the value, the distribution. It can be anything in the real line. So the probability that standard Brownian motion at time s is at y, let's say between y and y plus dy. I hope the notation is all right. That's the density function at position y of a Brownian motion at time s ds, the dy, right? And then, so otherwise, I have exactly the same thing, except that time of the new pair of independent branching Brownian motion, time is t minus s, and the starting point is not x anymore, but x plus y. That's the only difference. So that's this kind of product is what I used to quote u, except that time is t minus s, and starting position is x plus y. And of course, I have product of two, so that's the square of u, right? And that's it. So this is the value of the first piece. And the second piece, we already wrote it in red. That's e to the minus t, expected value of f x plus bt. That's it. So in principle, I know everything because everything is explicit. I only have a Gaussian standard, well, a Gaussian variable with the variance s, and so on. And from here, okay, I'm not going to do the exact computation because that's not really the aim of my computation. So you do some very elementary computation. You realize that, okay, the function as a function of pair of tx is very, very, very smooth, and you can differentiate, I mean, in whatever way you want. You can exchange the differentiation with integration and so on and so on. And at the end, what you get is that the derivative with respect to t is the. If I start here, it's just a heat equation. You know, that's what happens for just one single Brownian motion. And the difference, because of the presence of the branching, is that now there is a second part because I have the u square here minus u. That's the only difference. So this is for t strictly positive and x in the space. Yes? And of course, the initial value, the initial function by definition is just f. So this equation, it has a name called FKPP. So this is so-called FKPP. F for Fisher. KPP, so there are three Russian names. So Kolmogorov, Petrovsky. I think each time I try to write down the exact names, I made some mistakes somewhere. And Piskunov. So the two teams, I think their papers were published exactly in the same year in 1937, but for completely different reasons. Okay. So, just one remark. You realize that I don't use any particular property of the function f. So that's answer the question by Misha. So the function, the equation FKPP actually is satisfied by many functions f. So what I do need as properties of f is integrability, okay, measurability of course, and integrability. So for example, if f is between 0 and 1, then everything is all right. So the equation actually satisfied for more general functions f. And also, there is absolutely no reason why when a particle splits, it splits into two pieces. So the branching mechanism is also arbitrary, but you need some, if f can be big, then you need to have some good integrability condition. So if you have an arbitrary branching, then instead of u square, the square actually comes from the assumption that each time you split into two pieces. So instead of u square, now you get some over, so u to the k, pk, where pk is the probability that when you split into k independent copies. It's possible that p0 is strictly positive. That's also allowed. If that happens, it means that a particle just dies without producing any offspring. Okay. And of course, I mean, we are mathematicians. I mean, it's clear that this kind of parabolic partial differential equations has its own interests, and the system of branching Brownian motion somehow gives you an explicit probability solution to the equation. So if you want, you can try to study FKPP using branching Brownian motion, or you can do exactly the opposite way. You can try to study branching Brownian motion using FKPP equations. So just like in probability or in analysis, you can either directly study Brownian motion or the heat equation. Okay, maybe it's more surprising is that in physics there is a huge literature on FKPP because, well, I repeat what I'm told because I know nothing about that, because apparently in physics there are whole bunches of phenomena that satisfy the FKPP equations. So I'll just write a reference in case you don't believe me. So that's Van Saarloos. So in 2003 or 4, so he wrote a survey paper about 15 or 14 years ago, and it's a big paper. It has almost 200 pages, and it makes a survey of 453 papers. So I think that gives you an idea about how big the physics literature is about FKPP. So,
may I ask about the notation?
Yes.
What is called in this literature FKPP? I mean, you wrote the equation with u squared, then you replaced u squared with more or less arbitrary.
Yeah. Sure.
Is it also? What is the limit until which it is still called FKPP?
Oh, well, usually you can replace u squared by, let's say,
the same equation, but with more or less arbitrary
generating function.
Yes, you need to be a generating function, because otherwise you cannot. So but that's more or less.
This is what they call.
Yes. Yes, that's what I consider as. Yes.
This version with arbitrary branching. But
I would think so. Okay, so maybe one final remark. Well, is now I'm going to use the exact form of my function f. So in that case, so if I take f to be the indicator function of the non-negative line, then I realize that's, okay, I write it there maybe. I realize that I can write explicitly my two-parameter function u And as Misha said, it's really a probability, not an expectation. So with the choice of my function f being the indicator function of the non-negative half-line, then I realize that it becomes a probability. That's so everybody is, so it should be 0 unless everybody, the arguments in f, everybody is non-negative. So it means that the minimum of the xi should be greater than or equal to minus x. Yes? And I guess everybody is like me, somehow minus something doesn't look very nice. So Brownian motion, or you can take minus Brownian motion, is still a standard Brownian motion. So by symmetrical Brownian motion, you realize that it's nothing but the distribution function of the maximum at position x. Yes. So with my particular choice of f, I realize that okay, the solution, well, one of the solution u to the FKPP actually is nothing but the distribution function of the maximal position in my system of Brownian motion, and this is this relation between FKPP and the maximum of Brownian motion. This was due to McKean, but quite a long time later. So FKPP was in the 30s, and McKean was in the mid-70s. So that part was purely, parabolic partial differential equation. And here we have a very probabilistic representation in terms of Brownian motion. So for people in probability theory, suddenly FKPP equation becomes interesting more or less after McKean. Well, it's not the exact historic truth, because slightly before McKean, there were people studying branching diffusions in general, but I think the popularity suddenly increases after the historical paper by McKean. I mean, that's certainly true. Okay, so U of x is the distribution function at level x. So we saw that as a function of t and x is very smooth, and in particular, so I can draw the graph of u. So when t is 0, it's very simple. It's f, which is the indicator function. So t is 0, then u is, this is u0x. As a function of f, a function of x is very simple. When it's negative, it's just 0. And starting from 0, it becomes 1. And that's it. Yes, that was the definition. And actually, immediately after that, when time is strictly positive, suddenly, as a function of x, it becomes very smooth. And, well, it's very small, but it's strictly positive, and it's increasing, I mean, strictly increasing now. So once p is strictly positive, it becomes something like that, and it will never reach the position 1. So let me take some point, let's say the medium. So the medium, I give it a name, m of t. So this corresponds to 1/2. So mt is such that u of t mt is 1/2. It turns out that this solution, it's as if you are watching a movie. When t is sufficiently large, whatever you see is more or less identical. Asymptotically, it converges to something. The only thing which changes is the place of the graphs. So you're watching a movie which moves like that, but the images themselves almost never changes when t is sufficiently large. So what you see is something like and it moves at a certain speed. And so that's called a traveling wave solution. So it turns out that maybe here. So it turns out that if you put the x here, then there is a convergence, and it's uniformly in all x. So instead of looking at utx, I look at utx plus mt. And you let t go to infinity. It turns out that there is a convergence. The limit, I call it w, and this is uniformly in OX.
And you're writing plus.
Sorry?
Strange. I would like to see x minus m of t.
Oh, then you look at...
You center somehow.
Yeah, I center at mt, so that's why it's plus, right?
Okay.
Because if you take x to be 0, then this one gives you exactly 1/2. You cannot take minus.
Okay, then
yeah.
One can write m of t plus x. So.
Yeah, oh, if you want. Okay. And it turns out that w, as a function of the pair tx, w of x minus square root of t, square root of 2 times t, actually this solves FKPP. And it's absolutely equivalent to say that this is a solution of half of second derivative plus square root of 2 times derivative plus w squared minus w is 0. And this square root of 2, which is that square root of 2, is exactly, tells you exactly how things move. So if this is KPP, so KPP, I think that's in the 37. So they prove that m of t moves linearly when t goes to infinity to square root of 2. Okay, so far there is nothing very special, and we are mathematicians, so whenever you have some convergence, certainly a natural question is to know what's the rate with which it converges, and that was the question asked by Bramson in 1978 and in 1983 or 43. So Bramson proved that when t is sufficiently large, certainly the main term is linear. The second order in the convergence, usually it's a kind of central limit theorem, because the first one, usually we will call it law of large numbers. The usual central limit theorem tells you that the second order is square root. It turns out that here things are slightly different. You have a very nice constant, but the second term is not square root, rather it's logarithmic. And that's because of branching. So in the first paper, Bramson, I mean, he stopped here. He proved that it's minus 1 plus small o of 1 times this one. And then a few years later, he proved that, okay, it's a constant plus small o of 1. So this is a constant. It turns out that it's possible, well, it's not that hard to get the second term, but it's very, very, very hard to prove that it's a constant plus small over 1. By the way, so this was for branching Brownian motion, and at that time everybody said, okay, it must be something very similar for branching random walks, but for about 30 years, everybody believed that, but no one was able to prove that actually it was something universal for branching random walks. Okay, and maybe I would like to insist on the numerical value of 3. We are going to see why 3 is very important here. So for the moment, you only have my word that 3 has some very special meaning.
Square root of 2 comes if you replace your branching random walk with independent branching, right?
Yeah.
If the branching starts at time 0 and everyone goes independently,
sure.
That's what you get is square root.
Yes,
right?
That's true. The square root of 2, the first one actually almost has nothing to do with the branching. And as long as you admit that there is a whole bunch exponential to t independent Brownian motions, you already get the first term. So that's why the KPP result actually doesn't really reflect the fact that we are looking at a branching system. But the second one is special. If you use independent one, then you are not going to get 3. You get 1 instead of 3. So that's why somehow I wanted to insist on the numerical value of 3. But we are going to see in more details.
Maybe you can say to what extent this is universal with respect to branching mechanism. Do you mean here binary branching?
Yeah, it has nothing to. It's general. Well, you need some integrability things, so the moment should not be too high. I mean, there shouldn't be any explosion of moments. Otherwise, it's universal. But okay, when I say universal, actually, the square root of 2 certainly depends on the branching mechanism. So somehow I really need to take this one and then put it here. Even that was not true. Actually, what is universal is this one is universal. 3/2 is universal. It has nothing to do with the branching mechanism. But we are going to see that in more details. Yeah. So now I'm going to remove FKPP. Oh, okay. One last word about FKPP or about this traveling solution to FKPP. So McKean actually proved that. So in his famous paper connecting branching Brownian motion to FKPP, he proved that, and Lally and Selke a few years later, well, actually quite a few years later, and they proved that, okay, the limit, the traveling wave solution to FKPPW, actually there is a very nice probabilistic representation for this solution is the Laplace transform of okay, I have a whole bunch of symbols. Let me explain. C1 is just a constant, nothing very special. So C1 is strictly positive constant. And the D infinity is a certain random variable. So it's a random variable, and which is strictly positive random variable. So somehow, okay, you can. the product is still strictly positive. So if you want, you can really put this, taking the log of that one, put into the exponential, and then you realize that, okay, it's more or less, this is so-called the density function of the Weber distribution. So it's Weber distribution, but somehow with a random shift, which at log of this guy, actually is log of this guy divided by square root of 2. And we are going to see why, I mean, how this mysterious random variable comes into the picture, which I give as a very funny symbol d infinity. The constant C1 has nothing very special. I mean, certainly in my definition of MT, I took the medium, but if you take whatever quantile, let's say you take a place where it's 10%, let's say, then you exactly what I have said here is still correct, except that I have a different value of C1. Yes, I think, okay. So we are going to look at force. We are going to look at branching Brownian motion, but we don't assume that everything is Gaussian. So we are not going to take any Brownian motion or whatever, because when I tell you things like that, you get the impression that, oh, that's very special for branching, for Brownian motion. What I want to try to convince you is that it has nothing to do with Brownian motion. And Brownian motion is here totally innocently. What's important is branching. Yes. So we don't need anything Gaussian. So I'm not going to assume anything about the Gaussian distribution here. But for us, time will be discrete. And that's how we end up with the model of branching random walk. And that's what we are going to see after a break, let's say, of 10 minutes. Okay, so we started the first part, the introductory part. So before the break, we were looking at branching Brownian motion, and I hope everybody is convinced now that this is something which is closely related to the so-called FKPP equation, and moreover, there is a probabilistic writing for the traveling wave solution of the FKPP equation, which we are going to more or less to discover, not in details, in the setting of branching random walks. So now let's come to the main topic of these lectures, branching random walks. So the difference between branching random walks and the branching Brownian motion is more or less the difference between sum of independent random variables and the Brownian motion. So in the sense that for one, time is discrete, but that's not a big deal. And I think the main difference is that you don't assume any Gaussian distribution for the displacement. That's, but we are going to see that asymptotically you don't see much difference. Just like the usual central limit theorem telling you that sums of independent random variables, at the end you get a Gaussian distribution. Yes?
Should we also say that the difference is also like the difference between Galt and Watson branching processes and Bell-Van-Harris?
Oh, okay.
Or you don't think it's important?
It is, but somehow,
I guess now you lose the notion of time changes.
Yes. Yeah, that's
so that you come to the usual language of Galt and Watson.
Yes.
Branching trees with the generations and so on.
Yes.
It's still a big difference.
Okay, if you want. Strictly speaking, you are absolutely right. Yes. Okay, so when you look at the sums of, let's say, IID random variables, what you need to know is the common distribution of these random variables, right? And to define branching random walk, if you want to know the distribution of the system, you also need to know the common distribution of this thing. Here, the common distribution, because it's branching, instead of one single random variables, you need to know a whole bunch. I mean, this represents when a particle produces children, this represents the set of his children. So the number actually is big, capital N, yes? Okay. So for the moment, I'll call it random vector. Because, I mean, each component is a real valued random variable, right? Okay, so let's go. So this is time, this is space. It's exactly like what happened to the branching Brownian motion before the break. So at the beginning, let's say our system starts at time 0 with just one particle at the origin. Now time is discrete, so the next time is at time 1. Yes, and this guy dies and it gives birth to a whole bunch of children. With the example of Brownian motion, we always assume that the branching was binary, but I told you that, okay, the binary branching has actually, there was nothing very special about the binary branching. So now I stop assuming that it's binary, and it can be anyone. So you see, when it dies, it gives birth to a certain number of children, and they are their positions are distributed in space according to this random vector. Yes. So let's say there are 3 of them. So that's what happens at time 1. So it means that this 3-dimensional random vector has the same distribution as this random vector R, and that's it. Okay, so that's what happened to the first generation. Now you understand what happens, but all you need to do is just to repeat yourselves. So now at time 2, so this first guy is going to die, and it's going to give birth to a certain number of children, and their positions respect to the birthplace. Do you remember when, in the case of branching Brownian motion, the new one starts at the place where their father dies? Yes. So now, compared to this birthplace, you have a bunch of random variables. I mean, n-dimensional random vector, and their distribution with respect to the birthplace is identical to L, but it's totally independent of everything else. Yes? So let's say this guy, it has also a 3-dimensional random vectors. Now I come into a picture, into a technical point that actually capital N doesn't need to be a constant. I mean, the dimension of my random vector can be random as well. If you think that it's too complicated, then just keep in mind that for you, branching random walk, the dimension is fixed. But actually, it will not make your life easier, the fact that you assume capital N to be given. Okay, so let's say this one, it doesn't have any child. Let's say for this one, capital N is 0. If it happens that the random variable capital N with a positive probability it's 0, then it's possible that someone doesn't have any child. And this one, let's say there are 2 of them. Yes. And then the next one. Okay, now you see how this one is going to split, let's say, into 2 pieces. This one doesn't have 1. This happens with n equal to 1, and this one, let's say 2, and this one, let's say 1, and so on. Yes? So this is a generic graph for branching random walk. So let me repeat. Time is discrete. Every time when at each time a particle dies, it gives birth to a certain number of children, and they are distributed according to this random vector, whose dimension can be random. And that's it.
But all coordinates of this vector are identically distributed?
Oh no, there is nothing. It's just usual random vector, except the only thing which is more general than random vector is that the dimension is random. Actually, this is what's called a point process. But okay. But I don't assume anything about whether they are independent, whether they are identically distributed. Such assumptions don't make your life easier. If you assume them to be independent, you wouldn't feel that, okay, it makes your life easier. So why should you assume them? Okay. And in parallel, so this is time. Of course, the system keeps going on. In parallel, I will draw also the genealogy of the system. So at the beginning, so the genealogy, time is here. Well, time is actually the generation. So actually, I should look at, turn around this one. So this is the beginning of the story, the starting time, and this is the first generation, second generation, and so on. So at the beginning, there was only one person. And in the first generation, there were 3 persons. So all the 3 are the children of the initial particle. Yes? Then the first one has 2 children. The second one, in my case, doesn't have any child. The third one has 1. And then the first one has 1. The second one doesn't have anything. The third one has 1, I think so, or 2 and 1. So that's. I think
there
I
are 2 in the right hand side.
Sorry? There. Is that right?
No.
Okay. Okay, anyway, you know what I mean, right? But this is only genealogy. It doesn't, the graph on the right-hand side doesn't tell you anything about the positions of the particles. I only care about the numbers and from whom you were born. But I don't care about where you are in the space. I don't care. So the difference is that this is more or less the set of names in the class or in the laboratory. And here, not only I tell you the set of people in the laboratory, but also I tell you about their quality. The position in the space represents the quality. Here, I only have names. I say, okay, this guy is the father of these 2 guys, but I don't tell you how this guy is good or how bad he is. And here I have the whole picture, right? So that's the only difference between the 2 pictures. I hope it's all right. Yes? Okay, so the genealogical tree, I'll give it name capital T, T for tree. So according to my definition, for whatever position each time has k number of children equal to k, that's probability is exactly the probability that capital N is k, right? So actually this is the so-called Galton-Watson tree on the genealogical tree, right? If you don't care about Galton-Watson tree, if for you capital N is always a given number, let's say capital N is always 2, it's not a random variable, then it's just a regular tree. It's a binary tree, for example, if capital N is always 2, right? And that's it. Okay, so one line of notation. So X, okay, I know that my notation is not good. X is not a real number. X is a vertex in the genealogy tree. In my story of the class, X denotes a person, a student, or a professor. And this is the value of the student, the value of the professor, how good or how bad he is. Yes? So this is the positions of the system at time. So this is more or less the kind of notations I will be using for branching random walks. Usually we have, I don't know, when time is discrete, usually we have a sequence of random variables, and the time here is non-negative integers. Here the index is a vertex in the tree. That's the only difference. Yes? Okay, perfect. One assumption. I always assume that the expected number of children, so when the particle dies, it gives a certain number of children. I always assume that it's strictly greater than 1. So in terms of the Galton-Watson tree, it means that the system is supercritical. But it can be infinite. So this assumption is equivalent to say that with the positive, oops, it's here. This actually is equivalent to say that with the positive probability, the system is going to evaluate indefinitely. So it's so-called the survival probability. So there will always be someone in the system that happens with a positive probability. So that's something which is well known in the theory of Galton-Watson tree. And I think I'm going to say some more things about Galton-Watson trees in the fourth coming chapter. And that's more or less I want to tell you about branching random walks so far. So now maybe to give you some motivations.
Sorry, but
yes?
I think one should write some formula for V, that V of the next particle is
yes,
V
so
of the
V of this
particle.
is this one plus this one and so on.
I think it was to be written to make it sure that people understand. Because for you it is, and maybe for me even, it is so obvious what is V, but for those who are
okay.
looking at this for the first time, if you want to further write this.
Since you insist, yes.
Sorry.
This is for those of you who absolutely don't want to know what happens to branching random walks. All you care about is sum of ID random variables. I know that there are some of you who are like that, because at the beginning I was like that. Yes. So in this case, you get integer, which means that at least 2 actually, given integer. And moreover, you assume, let's say, n is 2. So each time everybody has exactly 2 children. Okay. And moreover, I assume that in this random vector, in this point process, they are all IID. I think that's Sasha wanted to have. Yes?
No.
Okay. And then you see that everybody is independent of everybody else, and if you want to know the value of branch random walk attached to this vertex, it's this random variable plus that one. So it's the sum of 3 random variables, each having the same distribution as xi1. Yes. So you see that it's just sum of ID random variables.
I didn't mention this particular case. I just wanted that it would be written that V of the child is V of the parent plus Xi. You did not say it even.
Oh, okay. Oh, sure. I really want to
it's
say.
It's so obvious for you, but not for other people.
Actually, the only reason for which I didn't want to write it is that the formula is not very nice. The independence is not clear because you need to.
Why independence? Just write that V is V of previous plus psi. What is it? Independent is not involved at all.
Yes, you need to tell
otherwise it is not clear what is V. Actually, you did not define V.
Oh, because I said already that when you die, you give birth to a bunch of random variables which are distributed as that one. Because I don't want to introduce.
If you insist not to tell it, so
I insist not to write. I already told you everything. It's for the beauty of the blackboard.
We here are not that formal as in France, so you may be sure that you will not be criticized.
Okay. Okay. Well, so maybe I should finish with that. So this one, it's usually I call it IID this. The model with the branching random walk with IID displacement. When you fix the number of children from the beginning until the end, and you assume that all the components are IID. So it's certainly a special case. It makes it makes everything absolutely clear. There is no doubt about the model. But from a technical point of view, I don't think it makes your life any easier. So if you prefer to stick to this case, why not? I mean, I have nothing against that one. And there are people who stick to this special place because everything from a mathematical point of view, everything you need to understand lies already in this special case. I mean, you don't lose anything particular. Okay, so now I want to talk about a few examples just to motivate you, and that will be the So I'll mention a few examples. Some of them are just branching random walks. Others are closely related to, but they are not exactly branching random walks. So I think I will start with the so-called Mandelbrot multiplicative cascade. So that was introduced by Mandelbrot. I think it was in 1974. So he was interested in the intermittency phenomenon in Kolmogorov's turbulence theory. And I don't want to say anything particular about that, about the motivation, but I'll give you his model. And what he gets is a stochastically self-similar measure on the line. And the subject actually has, for historical reasons, it also has an alternative name. It's called random recursive constructions. From a mathematical point of view, they are equivalent. So let me draw a picture. And you are going to see immediately that, okay, this is our branching random walk. So if you look at the standard contour set, you take the unit interval, and then, okay, that's the first step. Then you cut it into 3 equal 1, and you remove the piece in the middle. Oops, sorry. So you get the 2, and for the remaining 2, 1, you you remove the part in the middle as well. So in the next step, you have 4 pieces, and each of them you cut again the middle part and so on. So in the next step, you will have 3 pieces, and after n steps, you will have 2 to the n pieces, and so on and so on. That's the standard contour set, right? Okay, so if I draw the genealogy of this system, so at the beginning, when there was only just the whole unit interval, I write it just a dot representing this initial interval. In the next step, there will be 2 subintervals. So the value of this, and each time I will give a value associated with this vertex. At the beginning, the initial value is just the length of the interval, which is a unit. It's 1. The next one, I have 2 subintervals, each of length 1/3. So I'll put 1/3 here and put 1/3 there. So this is 1. To say that it's the product between 1 and 1/3. So the length of this interval is 1/3, and this 1/3. The next one, this one is going to split into 2. And I put 1/3 here, 1/3 there. So the length of these 4 subintervals is 1/3 times 1/3 is 1/9, and so on and so on. Yes? Okay, so all you need, whenever you take a vertex which represents a subinterval on the left side, if you want to know its length, you just take this, the multiplication of this guy times that guy times that guy, and everybody is 1/3. So you only need to count the number 1, which is the number of generation, and so on. Yes, there is nothing very special. Okay, so now Mandelbrot's idea is there's no reason why I should cut each interval into 3 equal pieces. Why should I? So I take a 3-dimensional random vector, let's say xi1, xi2, xi3, such that the sum is equal to 1. Okay? And then at the beginning, initially I have just the unit interval. And then in the next step, I'm going to cut it into 3 pieces, and randomly according to the value of this random vector. So the first piece, the length, the proportion is xi1. The middle one, which is going to be left out, is xi2, and the other one is xi3. So in my picture, xi1 is smaller than xi3. Yes? And then in the next picture, again, I'm going to cut this into 3 pieces, again according to an independent random vector satisfying the same law, and the proportion is satisfy the law of L, and so on and so on. And so on and so on. So exactly on the right-hand side, I can do exactly the same picture, except that now I don't have 1/3, 1/3 anymore, but rather it's a pair of 2-dimensional random vectors having the distribution of xi1, xi3, and this one as well. And this one. Each pair had the distribution of the 2-dimensional random vectors xi1, xi3. So if I want to know the length of an interval of this, represented by this vertex, all I need to know is take the multiplication of this random variable times that random variable, and so on and so on. Yes? So if I take the logarithm, everything, oh, I forgot to say that. I assume that all these random variables are strictly positive. Yes? There will be something left each time. Yes? And then if I take the logarithm of the lengths, then I'll get just an example of branching random walk. Yes, except that in my example of branching random walk, everything is negative because the length is smaller than 1. So by taking log, it will be negative. But there's absolutely no reason why they should be smaller than 1, why the sum should be 1. Why should you cut into, you can give bigger intervals. Why should you? the counter set, certainly you need to cut into smaller and smaller intervals, but there is absolutely no reason. So in Mandelbrot's story, I mean, there is no reason why the sum should be 1, and there is no reason why everything should be smaller than 1. Yes? So actually, you take just a three-dimensional random vector anyway, and there is no reason why you should take 3 actually. You can cut it into 4 pieces, and you cut it into a random number of pieces. Then you will recover the whole family of branching random walks. So you see that.
But if you drop the assumption that the sum equals to 1, then you drop the geometric interpretation.
Oh, sure, yeah, okay, because sometimes your intervals will be...
Cannot enlarge the interval, right?
Okay, you cannot, yeah, okay. My picture will certainly be wrong, but the contractions still, the contractions still make sense. I mean, certainly I prefer to contract in this way, and then you stay purely within the family of branching random walks. I mean, there will be no story of intervals. Okay, so that was my first example, which is exactly an example of branching random walk, no more, no less. My second example is also an exact branching random walk. And that concerns a family of special branching process in physics. I think the best known one is the Hirschsprung direct polymer on trees. So I think that was in 88. The story is very simple. So usually the study of direct polymers can be very delicate, but it turns out that on trees, things are very simple because trees have very special geometric structure. So I'll draw, let's say, a binary tree. Now I take a directed polymer. A polymer, you fix the length, let's say small n. It's direct, so the polymer starts life here, and it can be only directed downwards. Since it's on trees, there is no possibility other than doing this one. And it stops exactly at generation n, by definition. That's it, yes? So what I assume is that I put ID random variables on the edges of the trees, and so here is the ending position of my polymer. So x is such that x is in the generation n. So the absolute x is a vertex, right? This represents the generation of my vertex x. So the energy of the polymer is exactly this guy plus that guy, etc. plus that guy. So if I call it psi of x1, psi of x2, and so on, n is very big. This is psi of xn. Then I realize that the energy is just sum of ID random variables on this tree. So that's what we call it a branching random walk with the ID displacement, and that's it. Yes, so this is a very simple example of branching random walk. And so And it turns out that the same model, actually, it turns out that it can also serve as random environments of the so-called biased random walks on trees. Okay, sounds very technical. Oops, I think I should continue here. So this was a model introduced by Lance in the 1990s, early 90s. I think he wrote 2 big papers in the annals at that time. I'm not going to say any more about that because we are going to devote a special chapter on this model. And personally, that's how I got into the world of branching random walks, because at the beginning, I wanted to understand the model by Lance, the so-called biased random walks on trees. So for me, the original motivation was trying to understand the Lance's biased random walks, and I ended with all the other things. Okay, maybe I have a few minutes to.
5 minutes.
5 minutes. Okay, so very, very quickly, there were quite a few things. I think whenever people talk about branching random walks, and I remember that in 2012, so 5 years ago, Ofai Zaitouni came to give a mini course in St. Petersburg. I still remember the very beautiful poster of the 2 columns of the city, and he delivered a mini course on branching random walks and Gaussian free fields, and that was also well, that's, I think, one of the most important examples of things which are closely connected to branching random walks. So Gaussian free, okay, it's about 2-dimensional discrete time Gaussian free field, and it turns out that the structure of extreme statistics is very complicated. But somehow people managed to compare this structure with the structure of extreme statistics of branching random walks. And somehow that explains why nowadays, suddenly in the last, let's say, last 10 years or even less, suddenly people are able to say a whole bunch of things about extreme positions of Gaussian free fields, thanks to this comparison with branching random walks. And more generally, for so-called logarithmically correlated Gaussian fields. And in the continuous time, it's also connected to the so-called Gaussian multiplicative chaos. Okay, so I'll get multiplicative chaos, which will lead to the so-called Liouville-Brownian motion, but more generally, it's connected to the so-called Liouville quantum gravity theory, which is related to the large planar maps. So all these things are, they are not exactly the same, but they are quite connected to each other. So by the way, in early June, there will be a conference with the two main courses. The one is delivered by the Fields medalist Martin Herrer on the singular SPDE. The other one is by Jean-François Le Gall on planar maps. And these things are probably among the most exciting things which are being developed in these times. And there are quite a few other examples. You don't necessarily meet the keywords, the key expression branching random walk, but somehow you realize that, okay, that reminds me of something, and then you realize that by comparison to what you know about branching random walks, then you see what happens. It's just like sums of independent random variables. Somehow you realize, oh, that reminds me of sums of independent random variables. So maybe I should write just one word. So what I have in mind is a recent preprint I saw by again Belius.
Maybe we should put it higher because I see it, but maybe people behind don't see.
Okay. I think that was in December 2016, and they were able to prove a conjecture by number theorists, I think Fyodor Kitin and who's the third guy, about the maximum value of the Riemann zeta function on the critical line. Apparently, it has nothing to do with branching random walks, but somehow, I mean, again, Belius, certainly they are experts on spatial branching process, and somehow they were able to apply techniques of spatial branching process to say something about Riemann zeta function, which apparently has nothing to do with branching random walks. Okay, thank you very much.